Okay, so recording I think is running now. So we'll get started in a minute. Let me just reduce the size of this, and I can move it to this middle like that. Okay, so we'll start with the sets. That will be the first topic. So many of you will be familiar with this, and what I propose is that if you're familiar with it, you become part of the class as a resource person. If someone has a question in the chat, you respond to it, so that we get everyone on the same page from the beginning. So so um so we start with the definition. Usually we say that a set is a well-defined collection of objects. So well-defined simply means that if I have an object, I can tell whether the object is in my set or it is not in my set. So that's the idea behind well defined. Maybe there's one more thing that you can add. Sometimes you may want to say distinct objects, not just objects, but distinct. This is the reason for this is that there's also another idea on sets, or a concept behind sets, where you have, instead of sets, you have multi-sets. Multi-sets allow some elements to be repeated in the set, but we are not going to work with multi-sets. We just work with the usual sets that you're used to. So a set is simply a well-defined collection of objects. So for instance, a set can be the set of economic students in the University of Nairobi. So that becomes easy. I can quickly tell if I have an individual. It's a well-defined set because I can easily tell whether that individual is in the set or not in the set. So that's what we mean by well-defined. So in terms of terminology, if the objects in the set are called elements. So there's some notation also, which I think you're familiar with. So this one looks like an E. So this quantifier here means if X is an element of A, this is how we write it. This is a shorthand. So this will mean X, this object X is an element of the set A. So most of the time we shall use these capital letters to represent sets, and the small letters to represent the objects in the set. So again, if there's anything clarification you need, just put on your microphone and ask. Don't wait until the end of the class. So you should simply put on your microphone and ask. If you're moving too fast, you also say so. Then we can slow down. If you need us to review a certain point, you say so as well. So if you have a small set with just a few elements, you can write, you can simply list the elements and represent the set like this. So we usually represent a set using these brackets, the curly brackets. So when you see these brackets, this means a set with three elements. This one has three elements, the numbers 1, 3, and 9. A set can also have other objects. It's not just numbers. It can have other objects as well. But this is an example where the objects in the set are numbers. So if it's a simple set like this, as with a few elements, it's quite easy to represent it. You just list the elements in the set, separated by commas, and then on the sides you put the curly brackets. So these curly brackets is a notation for representing a set. We shall encounter it a lot as we go along. So we also cover the concept of inclusion. We say that two sets A and if you have two sets A and B, A will be contained in B if every element in A turns out to be also in B. So the notation for this is somewhere down here. I think it was misplaced. This is what it means to say that A is contained in B. So this is connected to what is up here. So A is contained in B means all the elements in A turn out to be also in B. So if you are writing out in shorthand, that means if an element X is in A, then it must also be in B. If you are doing this in terms of diagrams, if you have a set A, let's say if this is a set B, then you can have a smaller set inside it contained. So every element in A here is also inside B. So in that case, we say that A is a subset. A is a subset of B. So we can say two sets are equal if they contain exactly the same elements. So one way to check that two sets are equal is to check two conditions. So the following two conditions will help you check if two sets are equal. So if the two conditions are simultaneously satisfied, that is if A is contained in B and B is also contained in A, then we make the claim that the two sets are equal, like that. So these two together imply that A is equal to, like that. So I think this one is supposed to be capital A. So if A is a subset of B, it means A is contained in B. So we have checked the concept of inclusion and equality of two sets. A set is contained in the other set if all its elements also happen to be in that set. And they're equal if the two sets are contained in each other, like that. So this appears quite often in a number of the proofs where you have to check that two sets are equal. So this is quite an important idea to keep in mind, because it turns up quite often as you work through the mathematics. So I don't know if you need more detail than what I'm giving, but if you do, you please speak up. So I will get rid of this again, so we don't have the notes too dirty. Okay, so I'll move to the next page. And you also let me know if you think we should move faster. So sometimes if you have a subset of a set, you can specify that subset using the property or a predicate, a property that its elements satisfy. So how we do that is the following. We use this notation. So we'll have the curly brackets surrounding. Then on the left-hand side, we specify the element and where it's coming from. And on the right-hand side, we specify the property that the elements in that set must satisfy. So here, if you notice on the left-hand side, this means we are picking elements from the set of real numbers. So this symbol here means the set of real numbers. We shall look at numbers later, but I think most of you are familiar with this symbol to represent the real numbers. So X is a real number which lies between 0 and 7, that is including both 0 and 7. So this is a subset of a set of real numbers. So if you call this set A, it definitely is a subset. It is a subset of a set of real numbers. And it shows us how to describe a subset of a given set. So this is called the set builder notation. Now sometimes all you can do is describe the properties, the property that the elements in a set satisfy, and that completely describes your set, because the elements may be too many to write down or list. So sometimes this is a way this becomes sufficient in specifying, or more efficient in specifying your set, because then by just looking at the property, you're quickly able to tell if an element is in the set or not in the set. So again, like I said, if there's anything that it needs repetition, you let us know. So this is just another example. You see, like this second example is a good example of what I'm saying. Here you're considering all real numbers that are strictly smaller than -2. Yeah. And you can see that that should be a subset of all real numbers whose square is greater than 4. I hope that is clear. So you can check that. If you call this first set A and you call this second set B, if a number is in this first set A, the number will be less than -2. But if you square it, it will be greater than 4. Any number smaller than -2, when squared, will be greater than +4. So this set A is contained in B, because any element you pick from the set A turns out to be contained in the set B. Are we together? Good. Okay, so far so good. So the next concept we'll look at is intersection of two sets. So we will say that the intersection of two sets the sets are A and B, will be denoted using this. This is a shorthand to denote the intersection of two sets. But what this simply means is the elements that are contained in both sets. So if A is an element, so we can describe a set like this. So suppose this A is described using this. X is some elements in some set C which satisfies some property. So Px here is just some property that the element X satisfy. The second one also are elements from the same set C which satisfy a different property, not but they may coincide at some point. So the intersection will be all the elements in C that satisfy both properties. So I don't know if we need an example on this. Maybe we should. So for instance, just a simple example to illustrate this. So suppose this is our first set containing the elements 1, 2, 3, and K. So this is our set A. We can have another set B, which contains say 1, 2, 1 and 2. Then it has 7, 8, and R. So suppose that is the case. Then you can get the intersection of this. Intersection of A and B will simply be, so use this symbol as the shorthand, will be just the elements that appear in both sets. So the elements that are here and also appear here. And we can see one appears in A, it also appears in B. So we pick it. 2 appears in both A and B. So we pick it. And I think that's it. There's no more. There's no other elements appear in both sets. So the intersection of the two sets will be made up of just the elements 1 and 2. So we shall encounter a lot of this as we go along. Right now, the idea is for you to just get a good grasp of the concepts or get a review of the concepts that we shall be using. But it's really important that you get a good grasp of them because we shall be using these ideas along the way. So the next concept is the union of two sets. So we say that the union of two sets A and B is simply the elements that are contained in at least one of the two sets. So if you are to write that out using this set builder notation, it will be all elements that are in A or in B. So this concept can be extended to, I don't know if we need an example. We could apply that to our example up here. So if we want the union of A and B, we'll just pick the elements that are in at least one of the two sets. So one is in both, so that is fine because we want the elements to be in just at least one of the sets. Two is in both, three is in A, so that's fine. K is in A, yes, we can write it. 7 is also in B. We need them to be in at least one of the sets, so 7, 8, and R will also work. So you can see that the number of elements in the union of A and B is actually less than the sum of elements in A and the elements in B. We shall see why that is the case later. Because this one has 4 elements, this one has 5 elements, but the union has 1, 2, 3, 4, 5, 6, 7. So if you add 4 plus 5, you would get 9, but the union has only 7. So we will see how that counting works later, but it's something that is worth paying attention to, especially for finite sets. So the ideas we have mentioned before, the union and the intersection, were restricted to two sets. It's possible to extend it to more sets, a finite number of sets. So suppose you have k sets, you can also define the intersection of the k sets. That is, if x, you will definitely have a universal set. Maybe I can try to illustrate this with a diagram. So usually you will have a bigger set, which we call the universal set. And then we can define other smaller sets inside. So the intersection, if there were just two sets, the intersection is this part that is common. So this one would give us the intersection of A and B, assuming that the first set is A and the second set. So this first set is A and the second set is B. So if there are more sets, things will change now. The intersection now keeps getting smaller. So now if you have three sets, that's a third set. What is common to all the three sets seems to get smaller. Let me get a different color. So now the intersection becomes this part. It's a smaller part, and so on. That's just it. If you get more sets joining, it will become even smaller. What about the union? The union, if you have two sets, then the union of the sets is just you put everything together. All this and all that will make up the union. So the elements that belong to at least one of the two sets. You can extend this to more sets, so you just add more elements. In the elements that now are in the new sets and so on, it can keep growing, get more and more, you keep growing in size. So the union, generally, depending on how you choose the sets will grow in size, but the intersection usually gets smaller and smaller as you increase the sets. So another very important concept is the concept of the empty set. So so these are sets that contains no elements. Sometimes it's also called a null set. The empty set is just a set that contains no elements, and you may also call it a null set. So that is just so so this proposition we shall not prove it. I think you can try to do this as an exercise. Find out, get the proof for this. That becomes an exercise. So this you will do in your free time. So the empty set is a subset of every set. So you just work with that assumption. Usually we use the symbol, this symbol, to denote the empty set. We probably will use it at some point as we go along. So if two sets have nothing in common, if the intersection is empty, then we say that the two sets are disjoint. So disjoint is a definition of the term disjoint sets. Disjoint sets are simply sets that don't have any elements in common. Tuko pamoja? Okay, so here is a list of properties that are satisfied by some of these operations on the sets. Again, these ones we shall not prove. I will quickly go through them. This one says if you get the union of A with itself, the union of a set with itself just gives you back the same set. The same happens if you get the intersection of a set with itself. I think intuitively that should be clear. The order in which you perform the operations does not matter. So they commute. A union B is the same as B union A. That is also true for the intersection. A intersection B is equal to the intersection of B and A. If you have more than two, the operation of the union of sets is associative. So you could start with the union of the first two, or you could just do them randomly and do whichever way you wish, or you could start with the union of the last two. You still get the same collection of objects. The same happens for the intersection. You can start with the first two, do it in any random order, or start with the last two. You still get the same. So the operation here, the set operation, is associative. And here we can say that intersection is distributive over the union. So A intersection B union C can be split into A intersection B and A intersection C. So this can also be another good exercise for you to try to prove these properties. We will not prove them here because this is not our focus, but it's a good exercise for you to prove them in your own time. So also the union is distributive over the intersection. So if you have a union out here, it is distributive over the intersection of the two sets. So the next thing we shall define is the relative complement of a set B in another set A. And the notation is this: you have A with a backslash, then followed by B. So this means the relative complement of B in A. What that means is simply all the elements of A that are not contained in B. If you are to use diagrams to explain that, suppose we have two, let me make this bigger. Suppose we have two sets. It's the first one, that's the second set. B. So if you want the relative complement of B in A, you have to get rid of all the elements that are in B, just remain with those that are in A but not in B. So you knock out the intersection, basically. So this shaded part now is a relative complement of B in A. So if the intersection is empty, the relative complement of B in A is just A itself, because everything in A will be outside B. I hope that makes sense. Okay. So here is an exercise for you. I think since you have access to this document, you can look at it later and work on it. So these are, the next one is the famous De Morgan's laws. So the Morgan's laws simply say if you have the complement, I've not defined this. Let me make a definition quickly before we proceed. So suppose I have a universal set like this. Then I have a set inside here, call it A. So if this is my set of interest and that's the only set I'm interested in, this big set, and I have a subset within it, then as long as I'm aware what my universal set is, then I can get the complement of A, which is be all the elements that are not in A. So everything outside A, what I'm shading, becomes a complement of A. So for example, if I have a set U, let's just pick a small set containing 1, 2, and 3. Okay. So let's just pick a small set containing 1, 2. Maybe I can add something else. 1, 2, 3, and maybe 4. That's our universal set. Then I pick a subset of this. Let's say it contains only 1 and 4. So they will say the complement of A, since we know the universal set that it comes from, will simply be the elements that are outside A. So in this case, the complement will just be the elements 2, 2, and 3. Complement of A will be 2 and 3. But we're able to do that because we know the universal set. So you could also think of this as the relative complement of A in the universal set. But if you know this big set, then you can just write that as A complement, as long as there's no ambiguity about the bigger set. So that's how we define the complement of a set. It's pretty much the same as the relative complement, but here there's an assumption that you have a restriction on where the subset comes from, and you know exactly what the universal set is. So what our theorem here says is if you get the complement of a union of two sets, it's the same as the union of the complements of the individual sets. And the second one says if you get the complement of the intersection of two sets, this will be the same as the union of the complements of the two sets. You can see it changes. If you have intersection on this side, it switches to union on that side. If you have union on this side, it switches to intersection on the other side. So there's also another exercise for you here, which you can do later. Maybe I can illustrate the first one, then you can try to illustrate the second one in your own time. So suppose you have two sets A and B. I call this first one A and the second one B. Then I know their union is simply the shaded part. All these things I've shaded, that gives you the union of A and B. So if I want to get the complement of this union, let's see what happens if I get the union of the complement of A and the complement of B. So I will draw another one here and see if we end up with the... So the complement of A union B is what is not shaded outside here. But now let's consider this right-hand side term of this equation. So if I have A, this is A, then the complement of A is this shaded part. That gives me the complement of A, right? So I'll pick a different color. Then I have another set B. So what is the complement of B? Everything that is outside B. So the only part that is common to the shaded areas is the part outside these two sets. You can see that. I hope that makes sense. So now the only part that is common to this shaded area, the blue shaded area, and is it a brown or orange? I don't know. The brown shaded area. The only part that is common is the part that is outside these two sets. So the intersection of the complement of A, this other set was B, and the complement of B turns out to be the same as this unshaded area. I hope that makes sense. So graphically you can prove this, but it's possible to prove this using the rigorous mathematical techniques other than just graphs, drawings. But this gives you an idea. So you can try to use the same ideas to check the second condition, the second De Morgan's law. This can be extended also to more than two sets. The De Morgan's laws can be extended to more than two sets, but we'll not cover that now. So the next important concept we shall look at is a Cartesian product. So the Cartesian product, if it's possible to move your mouse to the side, I think some of the mouse is covering some of the content. If you are, you can move your mouse to the side. Yes. So we're going to define the Cartesian product of two sets. So the Cartesian product simply means you get all ordered pairs of elements with A from the first set and B from the second set. So this gives the Cartesian product of two sets. Maybe we can illustrate this. If I have A is a set containing these elements, I have 1, 2, and maybe some other element I call C. I'll pick a small one so that it doesn't take too long to write out all the elements. So suppose B contains 9 and C. So we wish to find the Cartesian product of A cross B. So the elements in this set will simply be ordered pairs. So the elements now will be ordered pairs, where we pick the first element from A and the second element from B. So we could start with all the elements that have 1 from A. So that will be 1A. And you will also have 1. 1C. That's one of the elements. Then you move to 2. We have 2A and 2C. Now all the elements will just be these ordered pairs. Then we can move to C. There we have C, A, and the last one is C, C. So we end up with a total of 6 elements. The number of elements in the Cartesian products of A and B turns out to be just these 6 ordered pairs. So ordered pairs means the order is important. So if you switch, it must stick to that order. The first element must come from A, and the second element must come from B. Second element in the pair. So if you there's a connection between the number of elements. Number of elements in the set A is 3. The number of elements in the set B is 2, and the number of elements in the cross product of A and B is 6. And the 6 is just the same as the product of the number of elements in A and the number of elements in B. So it's always possible, if you have a finite set or two finite sets, it's always possible to figure out how many elements will be in the Cartesian product if you know the number of elements in each of the two sets whose cross product you're obtaining. I hope that makes sense. So we'll go to functions, because we need functions to be able to describe. Thank you. So we need functions to be able to describe a few more ideas for sets. So before we say more about sets, we just talk about functions first. So this is another very interesting topic, because many times I I pose this question in class. I rarely get a correct answer for the definition of the function. Though I think, was it this week, I posed it and actually got a very accurate definition. For the first time, I got a very accurate definition in class. That was interesting. But let's get into it. So we start with the definition of a function. So a function f from a set A to another set B, we can think of it as a rule that assigns each element of A to a unique element of B. So that is one way to look at it. Another way to look at it as a function, you can think of it as a subset of the Cartesian product of A and B, but with some conditions, such that for each element A, there's only one such pair, AB. So once you have AB, you can't have another pair with A and a different element, say B. Once A is paired with B, it cannot be paired with any other element. So that subset also defines a function. So the set A usually is called the domain of the function, and the set B is called the codomain. So before we proceed, maybe this needs some illustration on. We want to make a clear distinction on what is and what isn't a function. So I think I need to retain this. We shall use that again. So we start with the first definition. The first definition says a function from a set A to another set B. So suppose this is our set A, and we have another set B on the other side. I'll just list the elements like this. So a function will pick elements in this set A, which is what we call our domain, and assign them to elements in the set B. Now the set B is what we call the core domain. So generally we label the rule. The rule is given some name most of the time. Many times the first encounter will be with the letter F to represent a function. So the rule that assigns an element of A to an element of B is given a name. In this case, we call it F. So let's give an example of a function. So we can have a rule that assigns 1 to A, assigns 2 also to A, assigns 3 to C, and assigns 4 to B. So this is an example of a function, because if you write this out as ordered pairs, 1 is paired with A, but it's not paired with anything else. This 1 is not paired with anything else as well. Let's go to 2. 2 is also paired with A, and it's not paired with anything else, so that's fine. It's assigned to A and only A. 3 is paired with C, and 4 is also paired with B. So no element. There's a question in the chat. Maybe I should check and see what it is. So we shall describe the range in a short while, but Nazrin is correct. They are different. The codomain is not the same as a range. In some cases they are, but in general, they will not be the same. There's a certain set of functions where the codomain turns out to be the same as the range. We shall see when that happens. So this is an example of a function because it satisfies the property that every element in A is assigned to a unique element in B. So let's see what can go wrong. If what would make it fail to be a function. So if in addition, now suppose we have a situation where I can delete this. I hope we don't need this anymore. Good. So now let's define another rule. So this rule say takes 1 to A. It also takes 1 to B. The rule also takes 2 to C. 3 is also sent to C. And 4 is sent to. So if you write this out as the ordered pairs, you have the following situation. 1 is assigned to A. You also have another pair where 1 is assigned to B. The same happens to 2. No, 2 is assigned only to C, that's fine. Then 3 is assigned to C. And what else? 4 is assigned to B. So this one will fail to be a function because you have 1 is not assigned to a unique element. 1 is assigned to A, and 1 is also assigned to B. So this makes it fail to be a function. So if you have a given element assigned to more than one element in the codomain, then that fails to be a function. So do not confuse this with one-to-one. One-to-one is a different idea. The reason for that, if you're talking of one-to-one, you can have a one. We will define a one-to-one function later. So for now, just understand that this definition is not or does not automatically mean the function is one-to-one. It just simply means that any element in the domain is assigned to exactly one element in the codomain. Another element in the domain can also be assigned to the same element. Like we saw here, 1 was assigned to A and 2 was also assigned to A. That can happen and it will still be a function. There's no problem. So this I hope this is sufficient. This defines this helps you grasp the definition of a function clearly. So this understanding this is useful because you will need this in calculus. You almost everywhere you go, you find functions. So a good grasp of a function will be useful. If you have any questions on that, is there any? If you have any questions on that, please ask. And those who understand what is happening, feel free to also answer in the chat. So I think the illustrations I've given there should explain what it means now for the function to be thought of as a subset of A cross B. So you can think of them that way because you can see all these elements are from the Cartesian product of A and B, but they are chosen in such a way for it to be a function. They are chosen in such a way that each if any element has 1 on the first slot, it will be the only element in the set. There will only be one element with 1, only one element with 2 in the first slot, only one element with 3. So the other elements which are left out, the other elements, so for instance, if you are writing out A cross B, in this case, there are many other elements you can add, say like 1 and C, but it is not here. So basically, this is a subset of the product, the Cartesian product of A and B. So a function is a subset, but with that restriction that for every element in the codomain, only one such pair with 1 on the first in the first slot will appear, with 2 in the first slot, 4 in the first slot, and 3 in the first slot. So you can think of it as a rule, or you can think of it as a subset of the Cartesian product. Whichever is easier to handle, I think that's the one you pick. But they are equivalent. The two definitions are equivalent. So so this one is just notation. For if we call the function f, so we can represent, since 1 is sent to A, we can denote that as follows. We can write it as f of A. So this will be read as f of A is equal to 1. Oh, sorry, f, that is not correct. I'll just delete it. So this one will be, since 1 is sent to A, we write this as f acting on 1, or f of 1 is equal to A. So this notation is also important to understand. That means f of 1 is equal to A. So the other way you can say this is that the image of 1 under this function is A. So A is taken as the image of 1. I hope that makes sense. But how we read this is that f of 1 is equal to A, or 1 is mapped to A under this function. The other way we can look at this is to say that 1 is a pre-image of A. So all those things describe this same statement. I hope that makes sense. Okay, if there's any question, please ask in the chat. You should be able to get a reply. So we've already mentioned that A will be called the domain and B will be called the codomain, as long as the function is taking elements from A and sending them to elements in B. So maybe just one more thing before I do that. I go back to this. The other way we can talk about this is we can say that a is a value of a function f at 1. So that's another way we can describe this. So a is a value of the function f at the point 1. We also have just one more example. We can also say that c is the value of the function at the point 3. That is f of 3 is equal to c. So that means c is the value of the function f at the point 3. That's another way of saying it. So there are multiple ways you can say it, and there are multiple ways you will encounter that in books. So it's important to know all of them. So we've said A is the domain, B is called the core domain. And we've just described what we mean by f of A. F of A will be taken to be the value of the function at the point A. So another new set that is important, we just need to get the idea. So the values of a function at all the points in a given set, all the possible values of a function for all the points in the domain is what we call the range of a function. So the range is a subset of the core domain. It can also be the whole of the core domain in some cases, but it doesn't have to be. So for instance, this one, in this example that we gave, the first example that was a function, maybe I can turn this into a function by removing this arrow. So if I do this now, it becomes a function. I can also remove 4 and say for it to fit my agenda, let me send 4 to C. So B is left out. There's nothing that is mapped to B, but this is still a function because if you write them out as ordered pairs, each of the values in the domain will occur in exactly once as the first slot in the ordered pairs. So this is also a function where 2, 3, and 4 are all sent to C. 1 is sent to A. So if you pick the values of a function at all points in A, the only ones that show up are A and C. So we'll say the range of a function will just be the set A and C. So the range are the values that are picked up by the function when all the possible values of a function on when it acts on the points in the domain. So in this case, this is left out. The range is simply A and C. Sometimes the range is also called the image of a function. So either the image of a function or the range. So I hope that makes sense to Gregory. You can see the difference. So this function only picks up A and C. So that is the range or the image of the function. So we if it turns out that the range is the same set as the core domain, then we say the function is surjective. Another word for surjective is onto. So a function is said to be surjective or onto if the range is just the same as the core domain. So if now we change our function, as an example, if this function changes so that say 2 is now sent to B, now the range of a function will have changed to the whole of B because every element in B has a preimage in A. Now the range is the whole of B and it's the same as the core domain. In such a situation, we say that the function is onto or surjective. There are more questions? Good. No, the comments. Okay, so we proceed. We go back to the definition. So we've defined the range, or sometimes we call it the image. So another concept, very important concept, is an injective function. So a function is said to be injective or one-to-one if any pair of distinct elements you pick from the domain, then that is if A, basically we're saying if A is not equal to A prime. So if this is a pair of distinct elements, if they are not equal, then their images will also not be equal. That is what we mean by a one-to-one or an injective function. So we could also state it as a contrapositive. We will not cover logic, but if you have a statement, the contrapositive of that statement turns out to be logically equivalent. If you have a logical statement, the contrapositive is logically equivalent. And what we have here is the contrapositive of the first definition. So the first definition says if these two are not, I'll just illustrate that. If we have P implies Q as our statement, then we can also, they have exactly the same, they are logically equivalent to this. Not Q implies not P. So these two are logically equivalent, and therefore they're interchangeable. So another way you can define an injective function is to negate this side, and that should imply that the negation of this side is also true. So if you change this to equal, it implies that this must be equal. So if f of a is equal to f of a prime, then a must be equal to a prime. And if that is the case, then the function is injective. So if a function is both bijective and injective, then we if it's both injective and surjective, we call it a bijective function. So maybe we can illustrate that a little before we proceed. So let's look at an example of an injective function. If I have, or we've seen surjective, so we can look at an example of a injective function. So here we have the domain, let's call it A. The codomain, we call it capital B. And then we have our function f, which sends elements from A to elements in B. So one-to-one simply means the following. Two like that. So this is an example of a one-to-one function or an injective function. So what this means, if I assign 1 to B, I cannot assign any other element in the domain to B again. That's what we mean by one-to-one. You realized in the previous function, we assigned, this was a function, but you can see 3 is assigned to C, but 4 is assigned to C as well. So this is not one-to-one. We have two elements on one side being assigned to one element on the other side. So this is not one-to-one because we have two here that are assigned to the same element. But one-to-one simply means if I assign 3 to C, I cannot assign C to any other element in the codomain. Now these were finite sets, and you can see that the first set A had more elements than the second set. So such a situation, means you cannot have an injective function, because once you map out the first three, the fourth one must share one of the elements in the codomain. So the only way you can have an injective function is if the number of elements in the domain is the same as the number of elements in the codomain, or less than the number of elements in the codomain. It has to be either equal or less than the number of elements in the codomain. So this gives us an example of an injective function, because one is assigned to B and there's no other element in the domain that will be assigned to B again. So this gives you, sometimes we shorten that as one-to-one, like that. One-to-one function or injective function. So to use an example, maybe what you may have met in class, I'll just get rid of this. So suppose we define, if a map, so another way we usually denote a function is to put f and say, put the full colon after f, we type a, then an arrow, and then b. So this means a function from a to b, where a is a domain and b is a codomain. So I will define, it's possible for a, the domain, and the codomain to be the same set. So let me define a function from, so we have a function from the set of real numbers to itself. So the domain is a set of real numbers, and we define the function as follows, that f of x is given as x squared. So is this function is it surjective? It is not surjective, because, for instance, so let's just write it out the way we wrote out the other one. We have the domain and the codomain are the same number. So what happens under this function is, for instance, a number like 2 will be sent to 4, right? Because any number you give this function, it will square it. The other one we can look at is something like -2. -2 will also be sent to 4, because if you square -2, you will get 4. So again, this is an example of a function that is not one-to-one, because you have two elements in the domain that are sent to the same element in the codomain. So this is not injective. Is it surjective? Let's find out. If you pick a number like -5 on this side, you need to be able to find a number on this side that is mapped onto -5. And that would mean that you must find a number which, when squared, will give you -5. But no such number exists on this side, right? So the range is not equal to the domain, the codomain. And therefore, this map is not surjective, because a number like -5 does not have a pre-image under this function. Is that sensible? So this is an example of a function that is neither injective nor surjective. It's a very naughty function. But you can restrict the range if you restrict the range. So for instance, if you restrict the range to maybe only the real numbers which are greater than or equal to 0 in the domain, then it becomes a surjective function. It will not be injective, because you still have 2 and -2 being mapped to 4. That fails to be injective. But now all the positive real numbers, if you restrict your domain to that, then the function becomes surjective. So sometimes by restricting the domain, you can change the nature of the function. Are we together? Are there some questions? I can see something in the chat here. Where? What was in the chat? I thought there were some comments. There's no new comment. So a function that satisfies these two properties is said to be bijective. So an example of so if we consider, suppose we consider a function from, let's consider a function from the set of integers to itself. So we define the function as follows. We take f of x to be equal to, say, x plus 1. So it picks an integer and adds 1 to the integer. So is this function one to one? So let's check. Suppose f of x is equal to f of y. What does this imply? This will imply that what is the value of f of x? It should be x plus 1. And what is the value of f of y? It will be y plus 1. Right? This is just a simple example. There are more interesting examples to work with, but let's just work with this. So what does this imply? From your knowledge of real numbers, you can subtract 1 from both sides of the equation, and the equation will be preserved. So if you subtract 1 from both sides, you end up with x is equal to y. So we have checked that if f of x is equal to f of y, the only way that can happen is if x is equal to y. So yes, this function is injective. Is it surjective? Surjective simply means if I pick any element from the codomain, I should be able to find a preimage for that element. So let's pick. So I pick an element x, or let's call it y, or z even. I'm happy with z. So I'll pick an element, let's call it z, which is an integer. Now I will draw my a diagram here. So I will draw the domain and the codomain. In this case, it's the same set. The domain is the integers and the codomain is also the integers. So what this map does, anything from here, it sends it to x plus 1. So the question is, if I pick any number from here, so suppose I pick a from this side, what number will be sent to a? If I pick a minus 1 from that side, then definitely if I add 1 to a minus 1, I will get a. So that means for any element I pick from the codomain, I can easily find a preimage. So every element a I pick from the codomain has a preimage. So nothing is left out by this function. That means my function is surjective. So this is an example of a bijective function because it is one to one, it is injective, and it's also surjective. Are there any more questions? For some reason, it shows there are some new comments, but I can't see them. I'm only seeing the older ones. Okay. Has anyone seen any new comments? Could be a problem with the software. So, have you seen? Does this make sense? So here is another concept. I think, let's see. Maybe we will this might be a good place to stop this section on functions. We can run through what is left on functions, then that might be a good place to stop for this class. Okay, we'll see what time is left after we are done with the functions. So there's another concept for functions where if you have a if for instance if you have a function from a set, there's more before that. I don't know whether I need to dwell on this. When if f is bijective, it's one to one and onto, there is an inverse function from the, now this is reversed. It switches the codomain and the domain. The inverse functions takes the codomain as the domain, and now they takes a domain as a codomain. They switch functions. So this inverse function is defined as follows: f of inverse for an element b in the codomain would be equal to a if and only if f of a is equal to b. So that's how we define the inverse. There's other ways of defining the inverse using the concept of composition of functions, but we will not do that in this class. But if you want that done, you can also let me know. I can do that. So, but we can illustrate this using. So this is a function that was one to one and onto, and therefore must have an inverse. The inverse simply means anything you pick from here, you can recover an element from that side, and the inverse also is a function. So there are problems if the function is not injective and surjective. Then the inverse, you may be able to recover the, you may have some map that sends you back to the domain, but it will not be a function. I mean, some relation that sends you back to the domain, but it won't be a function. Here is an example. If you have 1, 2, and 3, and A and B on this side, so 1 is sent to 2, 2 is sent to B, and 3 is also sent to B. So this fails to be an injective function. So if you want to get the inverse, you land into trouble because the inverse won't be a function. Because the inverse now reverses the direction. You start from this side going that way. Now the problem with that is that B will be sent to two different things. That fails to be a function now. So if the function is not injective, then if you try to define an inverse, it will not be a function. It will just be a relation. So I did not include any examples of finding the inverse of a function. But if you need that, you let us know. We can always add it. So now let's think in general. Suppose I have a function with domain, call it capital X, and the codomain, call it Y. So if I have a subset of the domain, then I can use this notation where I put the whole subset as the argument in my function. So this subset will be called the image of, this set, it will be a set, it will be called the image of A, and it simply consists of all possible values of a function for the points in A, where for all values, all such values. So this is called the image of a set A. So I will use an example here. If you have 1, 2, 3. So we have the domain and the codomain on this side. So let's take this as a function. 1 goes to, that's 9. 2 goes to B. 3 goes to C. 3 goes to B again. Say 4 go to C. 4 goes to C. So let's pick the set. So suppose we pick a subset of the codomain. The codomain was X. Sorry, the domain. Domain was X and the codomain was Y. So let's pick a subset of the domain. So let's pick just the numbers 2 and 3. So we try to find f of a. F of a is supposed to consist of all the possible values of a function at the points 2 and 3. So you simply check where is 2 sent and where is 3 sent. So 2 is sent to B. So we write it out. 3 is also sent to B, but you already have B. So that is all. This is the image of the set A under this map. If you take, say, A to be 1, 2, and 3. Suppose A is 1, 2, and 3. Then you can find the image of the whole set A as follows. So the image of the set A will simply be find out where all the points of A are sent and write them out. So you can see 1 is sent to 9. So 9 is one of the points in the image. 2 and 3 are both sent to B. So the image of the set 1, 2, 3 consists of just 9 and B. Does that make sense? What has happened? Looks like what happened? Everyone was knocked out of the class. Okay, that is strange. Something went wrong. I think looks like people were knocked out of the room. Where has everyone gone? Samuel, is the class too long? Maybe we should shorten the time for the class. So my proposal is I think we'll stop the class there. We pick it up from there next time. I've tried to move fairly slowly. I hope we'll continue tomorrow. I hope that speed was okay. But we'll pick it up from there tomorrow. Likely because I can see most people have left. Why? I don't know what happened. I'm not sure.